Hello, my name is Eric, and today we're gonna speak about visual programming for structural engineers. And before we begin with the topic, I would like to give some information about who we are, what we do. And in essence, we are an IT company offering software, trainings, and programming services for Baltic companies working in the construction sector. Here you can see some of the companies with which we have certain cooperation in terms of visual programming from both Latvia, Lithuania, and Estonia. In general, when we speak about trainings, we always speak about practical hands-on trainings. Typically, these are master classes, up to 8 people, during which we focus on really practical things. Regarding services, we offer different type of programming. Basically, what we do, we identify the problem and try to figure out the best approach to solve it using either Grasshopper visual programming, which we will speak today, either classical programming, in which we specialize in C#. We also have a wide range of different softwares, which we pre-test before we actually show them to the market and make sure that they actually solve some problem. And one of our core capabilities specifically is in the sector of structural engineering. This is also why we have joined here today. For this webinar, Jānis Marcinkēvičs will speak and overtake the main topics. He's our most experienced structural engineer, and he's an IT specialist. He also is a lecturer who provides different type of the trainings for all type of users, both advanced and beginner level. Okay, so I will give word to Jānis. Jānis, can you take it over?
Can you see my screen?
Yeah, I can see your screen. I can see you as well.
Good, good. All right. Hi, everyone. Thanks for joining. So today's topic is about visual programming, Rhino Grasshopper specifically. And the goal for today is to give a sort of broad picture of what's possible. Today, we are not going to dive into very technical details of how to do stuff, but rather to show what's possible. We are planning next webinars where we can go more into details and actually show how to do stuff. So, but about today's agenda, first I'm gonna give a short introduction to visual programming and Rhino Grasshopper to those who probably do not know yet anything about that or hasn't tried yet. So very brief introduction. Then I'm going to talk a bit about the finite element calculations, what we can do in the Rhino and the Grasshopper, Tekla structures and Grasshopper, how we can link those two. There is actually two type of links now. One is this Tekla live link, and other one is the Grasshopper component in Tekla. So I'm gonna talk and show examples of both of those. Then Grasshopper and IFC files. So this is probably not exactly structural engineering related, but nowadays when almost everything is in 3D, so structural engineers deals a lot with IFC files. And last but not least, how we can share the data with others using some modern technologies like using cloud data. So let's start then. So what is parametric design and why we should use it? So probably nothing new to most of you, but so we start with some initial parameters that could be geometrical information, points, curves, some 3D geometry, some number inputs or text inputs. Those are parameters. Then we set up a set of rules. So that could be some algorithm, or we can put that in some plugin or whatever. So there is some functionality in this step, which works with our initial data and comes up with the output data. And then the output data can also be some 3D geometry, 2D geometry, some data in tables, whatever. So, and if the process is truly parametric, then we can manipulate this output data just by changing the input data and not touching the algorithms and functionality in the middle. So, and this approach is, of course, great for if there is some changes coming. So once we do this and then some changes come, so it's very easy to get the desired result. And if you're talking about the Rhino Grasshopper specifically, it's also great for all kind of complex geometries. So yeah, there is many parametric tools on the market. So in fact, probably most of you already work in one way or another parametric tools. Most of the softwares that the structural engineers use these days are parametric. But Rhino and Grasshopper takes this to the next level using visual programming, where we can set all kinds of user-defined rules for parametric design. And on top of Grasshopper and Rhino, we have available lots of plugins, which really allows you to customize your algorithms for very, very specific needs. Yeah, why visual programming at all? So probably I don't need to explain why programming as such is very useful, because we use computers, we use software, and everything is programmed there. And if we have skills to program something on our own, that gives a lot of advantage to automate things. But if you are a structural engineer, then probably you don't have time, unless it's your hobby, to learn conventional programming. It's not that easy and not that fast. And so if you're talking about the visual programming, it's the learning curve for that is much more shallower. So you can pick up this visual programming much more easy than let's say some C++ or C#. That probably is the main thing why you should use the visual programming. And if you're talking about the Grasshopper especially, so then it's particularly good in all kind of geometry, 3D geometry related things. So there is a lot of tools, especially for this type of things. And another great thing while working in Grasshopper is that you get instant feedback. You can use the Rhino as a viewer and instantly see what is your algorithm doing, going in the right direction. Are you doing the right things? Which would not be that easy probably if you use some conventional programming methods. So next, let me jump to the software and show a couple of examples. So those who has been using Grasshopper, probably nothing new, but just to give overview how does it work. So here I will create the simple steel bridge using just the Grasshopper algorithm. So first I start with defining 2 points, 2 nodes. Between those two there will be a bridge structure. So I set the parameters where I can define the span of the bridge from the distance between those 2 points. Then between those 2 points I create the lines which will represent the axis for the beams and suspenders and braces and so on. And of course, as it's parametric, if we change the initial parameters, the geometry of the bridge changes, the width the height, the curvature of those arcs, and so on. So when I have all the axes set, I can assign the cross sections to those members. So using various tools, I assign different cross sections to different members. So, and of course, if I would now change the initial parameters, I don't need to reassign those cross sections. They are there. So that's a very simple example. And next, I'm going to jump to finite element calculations using Rhino and Grasshopper. One thing that you can do is utilize the existing links between the Rhino and Grasshopper and various finite element calculation softwares, as for example, Global RFM or FEM Design or Autodesk Robot. And there is really a lot of those links already existing, and then mostly they are being developed by the those finite element calculation software components themselves, so they are quite well done and stable. So you can benefit a lot from them. And let me show a very quick example. Here I have the same bridge there, and I can I have opened the empty RFM model in the same time. So from the Grasshopper RFM menu, I set up a few components and instantly can transfer all the data to RFM model. And in the same way, I can choose the points where I can, for example, add support there. So, and again, there is just one component in Grasshopper, and I get the supports in RFM model. And of course, if I change something in the Grasshopper, it instantly changes also in this case, RFM model. So that's one example. And then if you would like to stay just inside the Rhino and Grasshopper and not use some third-party softwares, there is a tools that allows you to do so inside the Rhino. One of such tools is Karamba 3D. This comes as a plugin for the Rhino and Grasshopper, so you must install that separately. Yeah, but once you do so, then you work just inside the Rhino and Grasshopper. Karamba 3D allows you to calculate 1D members and 2D members, so you can calculate the beams, frames, trusses, and also all kind of shell structures. And as an output, you can get forces, of course. In the 1D and 2D elements, you get the stresses, you get the deformations. You can calculate the local and global buckling shapes, and you can also do the code checks for steel members according to your code. And let me show one quick example. So here I have the same bridge model that I showed earlier, and I have the center lines of the elements. And then from the Karamba menu, I can choose the cross section. So Karamba comes with a large cross section library for steel members. So I choose the cross sections. Then I can choose the loads. So for example, in this case, I set up the self-weight, which depends on the cross sections that I assigned previously. Then I can assign some additional loads, in this case, the surface load or mesh load. So I just need to define the direction of the load and the magnitude of the load. So let's say 15 kilonewtons per square meter. And so I need some surface or mesh to add that too. So I will just utilize the beams that I created earlier, loft some surface through those. And then now I have the surface to add load to. And let's just assemble the model. You can see that the load is being transferred to the beam. So just the direction probably is wrong, but the great thing about the Karamba that you can use the identifiers. You can set the identifiers for all the elements. For example, I have the setup that there is a cross beams, and I just attach this name there, and it knows that load should be distributed just between those cross beams and not the main beams. And of course, if I change now something, the load gets recalculated automatically. And then I can add some more elements, as for example, hinges between the elements. And again, I assemble that, and I can again use the identifier. So I can tell that, okay, I want those hinges to be just to the cross beams and suspenders and diagonal bracings in this case. And I feed that information into the hinge joint component. I set the degrees of freedom for those hinges, and I connect that to model assembly. And that's it. I can calculate the model. And in fact, by default, it's being calculated in the background. So I change something, and it's instantly I get the feedback. So here I can view the deformations. I can change the scale for those. Then I can view all kind of results, the stresses in the elements. I can view all kind of internal forces, of course, the moments, bending moments, the shear forces on all directions, axial forces. I can display the numerical values necessary or just the diagrams. I can set up the legend to better understand the scope of those internal forces. Like that, I can, when the calculation is done, I have forces, I can do the code check. So as I said, we can do the code check according to Euro code 3 for steel members. So just I input the model and it's done. I already have the results. So the question is just how we view the results. In this case, I will just add the text panel. So I have the utilization ratios for all the members. So by those numbers before them, I can identify the members. And I can again use the identifiers, for example, and check just the arc members in this case. Other thing that we can do, we can calculate the buckling shapes. We can calculate one or many buckling shapes, global, local buckling shapes of that bridge. Of course, if you use this Eurocode check component, the stability of elements is being taken care of. Yeah, but I can calculate the global buckling shapes as well if necessary. And when I have the results, so I can view that in Grasshopper Rhino itself, or I can export. So I'm going to show a quick example how we can get those results to the, for example, Excel spreadsheet. In this case, I have empty Excel spreadsheet, and I use Excel write component. I set up the data, how I want it to be exported. So what goes in which columns, what goes in which sheets in the Excel workbook. So I set up the file, the sheet name, and then the name for the columns, so that the Grasshopper knows which data to send which column. And then I just run the component. And that basically is. And then there is two types. How can you can do this live when something changes in the Grasshopper, it instantly changes the Excel, or you can do is like when the user says to send the data, then only then it's being sent. And here I have the Excel spreadsheet with all the internal forces of the elements. And of course, you can utilize that Excel export, not just for the Karamba forces, but for anything that you can imagine. So that was Karamba 3D. I encourage you to download it from the Food for Rhino and try it out. And the next topic, which is probably my favorite part of the Grasshopper, it's called Kangaroo. So it's a set of tools that allows you to do all kind of physics simulations inside of Grasshopper and inside of Rhino. You can use it for FEM calculations as well. You can do the form finding with it. You can do all sorts of optimizations with it. So it's a really neat tool. So, and let me go to the software and show a couple of examples how does it work. So here I have the Rhino model and a Grasshopper file open here. So let me start with a simple example. I will start with the simple curve here, and for that I will draw this curve inside of Rhino. So I choose the line component or line command, the Rhino. So 1 point, second point I have line. So I can reference this line inside of Grasshopper. So I have a line. So next I'm gonna divide this line into, so to speak, finite elements. I'm going to use divide length component. Here I will decide the length of those divisions. Not thinking too much about the units now. So just very general example. Through those points now, you can see there is multiple points. I will draw a polyline through them. So polyline, and I will explode that polyline into finite elements. So now I have many segments, this polyline. And then for each of those, I will create the beam element. So from the Kangaroo menu, you can choose the beam component here, and it requires start frame and end frame. So on each of those small finite elements, I need to set the frame on the started element and the end. For that, I can use the perpendicular frame component. So for the start, for the end. So, and to tell that it's start or it's end, I need to provide the number here. So the start will be the index 0, the end there will be a index 1. So I have the frame on the start and on the end of the element, and that goes into the beam. For the beam itself, I do not specify the cross section, rather I specify the properties of the cross section and material as the modulus of elasticity, the cross section, the moments of inertia in different directions, and so on. As a default, it's 1 everywhere, so I will leave it like that. So, but of course, you can use some algorithm to calculate those properties from your cross section. If you define or draw the cross section in Rhino, you can easily calculate these properties there. And so we have our beam elements there. As a minimum, we would need some supports also the ends of the beam. So I'm going to use the support component like that. And I need to choose the points which will be supported. So use the point component there that goes in here. Use the same for the target in this case. And we need to choose the degrees of freedom or fixed direction for this support. So I'm going to use the simple on or off switch there. I will set that on, and I will use it for all directions, all transitional directions, and all rotations. And then so I will get the completely fixed type support. And the strength, so So it's you set up basically what's the strength, can it move or can it not. So if it's not non-movable support, so you just put some really large number compared to those, for example, beam properties. It should be large, but I will leave it 100. So I think it should be enough. So it will be like a fixed connection. So that's one support. I'm going to copy this. It will be the second support, and then I just need to choose the point. So I will set that one support point here and another one on the other end of the beam. So I have two support points there. And what else? So probably I need to add some load. So I will use simple component for adding the load to specific points. So again, I will choose the point component to set the point. So the point could be, in this case, in the middle of the beam. So, and then I need to define the direction of where the load is acting in which direction. So that will be the Z direction, and then the magnitude of the load. So say just -1. So as I said, I'm not thinking now about the units. So it's whatever units we use there. So we of course should think and use the same units for the loads, and then same units we should think here, and also for the length of the beam and so on. So those units must be compatible. And that's it. I have all the information I need to calculate the model. So let's merge those initial data together. So I will use the define component for that. It's not mandatory, but it's good to use. So you will have the better control of the results afterwards when you are done with your calculation. So I will input the beam, and all the rest I will input in one branch there. That. So I have all my input data in one place, and I can do the calculation. So Kangaroo has multiple solvers. You can use whichever you like for your specific needs. So I'm not going to explain that much what the difference. So I will use this simple solver, and there goes the input data there. There I can put the simple button to reset the calculation. Right one. So if something changes, simply reset the calculation. So this is the top view. So you can't see much, but if I rotate that, so you can see that. Okay, for now those are just the points there, but you can see how it's deforming. So if I would like to see some line instead of points, I use some polyline here after the calculation is done. So I have the points here, so vertices. So I have this kind of deformed shape. So it's a bit strange, but I guess there is fixed supports there, so it could be something like that. All right, that's quite simple. So let's create some bit more complicated geometry there instead of this beam there. So I will draw some frame there. So again, so I'll start with the line. Let's draw a frame like that. And then let's add probably something in the middle here. So some small console there, some short console like that. All right, so I have a frame like that, and for this frame, I will use a bit different approach. I will not load it directly with the load. So, for example, I will delete the load. I will change the input data here. So let's set multiple curves like that. Okay. I have curves there, and let me check what's wrong there. Make this a bit longer because of that division. Better. All right, and I have now this frame there, and calculation is already running in the background. But here I have prepared some tools to visualize the data. It's simple scripting components just to better organize the data. So I will just output data from the solver here, and then I will use some review components to add some 3D shape, for example, to the elements itself, some general shape. Of course, I could assign some double T or I beams or something, but now it's just some default shape. Give some volume to the model. All right, and then in this case we didn't set up any load, so I will use the component that's called grab. This one, grab component. I will input that alongside with all other data here. And what it component allows us to do is to grab the model and stretch it and bend like that to test all kinds of loadings, like very rapidly. So I don't need to set the load, but I can quickly estimate how that structure will work if I, for example, add the load in this corner and that direction. So give that kind of instant feedback. And here I can use also the preview components to, for example, to show the diagrams for all kinds of internal forces. So I will, for the moment around x-axis, I will add the color there. Let's set it to be red. And copy that other direction. I will add some different color there for movement along the y direction. So let make it green like that. And then I have the separate output for the torsional forces. So set that. Okay, let it be green as well. So let's test it. So now I bend something and I immediately have the diagrams for the bending moments. You can see those spirals. Those are for the torsional moments. If I twist something, so I have torsional moments. So I think this is great tools to create some truss and test or visually assess the deformations, so without setting the loads. And then of course, after that, you can do more precise model and actually add the loads. I really like this kind of approach to prototype or quickly estimate things. So that's one example, and let me do another one. I'm gonna delete this example. I'm gonna delete geometry from the Rhino as well. Let me jump to the next example. I mentioned before that you can use Grasshopper and Kangaroo for form finding. So you don't have to have some expensive software to do all kind of tensile structures. You can use just Grasshopper. And in fact, the Kangaroo comes with a standard installation, so you don't need to install Kangaroo separately. It's in this standard menu. So in this case, I'm gonna start with the Grasshopper, not with the Rhino geometry. I'm gonna create a simple mesh, simple planar mesh. So you immediately see it's there. So I will just leave the size and everything. Of course, you can change that as well. So that will be our mesh. I will extract the corners of this mesh using mesh corner component from the Kangaroo menu. So I input the mesh and it finds the corner points there. So you can set the minimal angle, what it's considered a corner. So in this case, finds those 90-degree corners there. I have the corner points on, so on those corners I want to put the supports. So either I use the support and there is a different component called anchor. I will use that one. So there's the input points, and I will set the point component here. And I will set the target points. So those are points that comes from this mesh, but I will set on top of those, I will set another points. Let me select the points. 1, 2, 3, and 4. So, and I can change the location of those points now. So let them be like that. So I have my support now, and next I need to tell something about the structure itself to give some stiffness to that. And there is a number of tools that you can use for that. In this case, I will use the edge length component. So I will input the mesh there. And then for the length factor, I will set the number slider with the default value on 0.5. Again, I'm not now thinking about the units. So it's kind of unitless moment. You can put the strength, so that would represent this material, how, with what effort, how far you can stretch that, if that's some kind of tensile material, some tenton or something. And so now I have everything that I need for calculations. Again, I'm gonna collect all the data in one place. In this case, I will use merge component. So here goes the mesh data, here goes the support data, and now I can solve this model. I'm going to use the same simple solver. I'm going to set also the one button to reset the model. You can immediately see the result. So I'm changing the position of these points, for example, and the Kangaroo solver finds the optimal shape based on those material parameters, structure parameters that I have set there. So if I would change those, you can see that the structure also changes. So for now, those are just the lines and the points. If I would like to assign some mesh again or surface to them, I can do that. Use mesh from lines component. I put here the lines. There I have the mesh again, but now it's deformed. Assign some preview there. Like that. And if I would want to really prepare probably some documentation for manufacturing, it's very easy to add some cutting patterns there and then generate 2D drawings for those cutted pieces, so that you can really create this kind of tensile structure. All right, let me jump back to the presentation. That was Kangaroo tools. Next one about the Tekla and Grasshopper links. The first one, which been there already for a while, is Grasshopper Tekla live link that allows you to send data from Grasshopper to Tekla and back from Tekla to Grasshopper in a live, so to say, live mode. So you have open both Rhino, Grasshopper, and Tekla. You create something in Grasshopper, it immediately appears in the Tekla, and vice versa. You can use this for creating geometry. You can set up the user-defined attributes in Tekla, both create the attribute itself and then fill the values there. You can extract the information from Tekla to do some bill of material if you want to do that in that way, and then you can add profiles to profile catalogs from let's say you have some DVG files or with hundreds of profiles. You can in one click you can send all that information to Tekla profile catalog. That was this approach that's there for a while, and then there is completely new thing from Trimble. It's called Grasshopper component for Tekla. So what it allows you, it utilizes this tool that's called Rhino inside, or set of tools that allows you to run Rhino and Grasshopper inside of other softwares without actually opening the Rhino itself. So if you have already some Grasshopper algorithms, you can use this Grasshopper component inside of Tekla and then run them inside of Tekla as normal Tekla components without caring about the Rhino itself. And let me show how does it work. So I'm gonna go to the Tekla here. We have empty model. I will open the component catalog and I will search for the Grasshopper component. So it's there. It's open. And here you just load the Grasshopper script. I have Grasshopper script here. It's a simple parametric truss. So it loads the script, and the good thing about this is that it actually works faster than this live link. Here you can see that I have all kind of parameters there. That's probably not right, because not all the sliders and not all the text inputs that's inside the Grasshopper is meant for users to change. So if I don't like that, I can go again to the Grasshopper. I can open same script. So I'm going to go and open this this parametric truss script which I have here, and I can tell which parameters I want to change inside of Tekla. And you can do that in a really simple way. You just choose the input data, you group them, and you must assign the name tab here. There's other things that you can do, but one of them is you can assign tab like that. You save the whole thing, close, or you can leave it open as well. And now if I would go, now I will delete this one. Now I again go to the component there. And now you can see that there is very few of those inputs left. And there is only those that really is supposed to be changed by the users. So let me set up something, some parameters for the truss. So I have some height of the truss on the sides, height of the truss on the middle. I can set the okay, when it's all said and done, you can choose the input points. So that will be the first point, let's say that will be the second point, and you have your truss component. And if you change something here, for example, I want to be a bit higher on the middle, changes just like that. So I can change the type of those diagonals. I can this side, I can put the middle section or top member to be the straight one, and stuff like that. So if you already have some Grasshopper scripts, it's very easy to turn them into the Tekla components. So that's really cool, I think. All right. Let me go back to my presentation. Yeah, and then I'm going to show also this link tool, just to give you idea if you haven't tried that already. So here I have the same bridge model, so I can choose the beam component from Tekla menu. I can assign profiles to those elements, so I can access the Tekla profile catalog, choose the profile for arc members. I can do the same for the position of the profile. So very easy to change. So then I go on and set the profiles for all the elements, and they are instantly sent to Tekla. I can also add the components between the elements. So if the component type is connection, so I can connect the elements. So in this case, I will connect those suspenders and the main beams with some simple components. So again, I can access the component catalog. I choose the right component there, and we have all the connections there. And then I'm going on and copy this whole component. Just change the input members, the main elements, and the second elements, and we have the components there. And also you can control the parameters of components as well. If you know the name for specific parameter, so but you can find in the attributes folder, in the Tekla model folder. So I set the name for the specific attribute. I put some number slider. I connect that to the component, and this way I can control the how many bolts or rows of the bolts are there. So, and this approach works not just for the connection types. it can be used for all kind of components. Here in this example, I will read the center of gravity of the elements and set in equal distance from the center of gravity this kind of lifting lugs. So if the center of gravity element changes, those position of those lugs also will change. So that's one example, and let me show another very simple example. As I said, you can use the Grasshopper to generate all kind of complex geometry. As you probably know, the Tekla is not very good to dealing with all kind of non-standard shapes, some double curved surfaces and so on. So you can use Rhino and Grasshopper for that. In this example, I will generate the ground surface based on 2D topography DVG file. So I can read the point coordinates, and I will read the text attributes that are closest to each of the points. So through those points, I extrude the surface, generate the surface. And then from this surface, I can extrude and get the 3D solid model. And this model, with one simple component, the item component, we can turn into Tekla item. So if you now go to Tekla, we have this kind of solid model inside of Tekla. That would be almost, I think, impossible to create something like that inside of Tekla. So all those three things that I showed so far was quite simple, quite fast to do in a matter of minutes, if not a matter of hours, but anyhow quite fast. So that you can use the Grasshopper to create more advanced things. And in this case, it will be the script for creating the stairs based on 2D DVG file, 2D geometry. And this is something closer to like real software or plugins. It takes much more, of course, than just the hours. It's quite time consuming, but the result is good, and the result is close to like standalone applications. So, and if the scripts gets quite complicated like this, it makes sense to create the user interface. So Grasshopper allows you to create the custom user interface that simulates like standalone application like this. So, and you don't have to interfere with the Grasshopper components itself anymore. So here I said the location in Tekla, I said the location in the DVG file, I pick up the outer line, the inner line of the stair, I choose the step lines in no particular order, they will be sorted for me, and that's it. I go to the run script, and geometry gets generated inside of Tekla, and you can add whatever you want, some kind of covers for the steps if you want. You can change the connection details on the top from the bottom of the stairs. So there is really no limit what you can create with the Grasshopper scripts. You can develop these kinds of like full-scale software, full-scale plugins for Tekla. And yeah, you can change the input data, for example, the height of the stairs, and it will always follow. All right, that's about the Tekla and Grasshopper links. And next, I'm gonna very quickly talk about the IFC files inside of Rhino and Grasshopper. I'm going to Grasshopper. I'm gonna delete this for now. And I'm going to import the IFC file. So let me quickly go back to the presentation. So there is multiple things that you can do with IFC. For start, of course, you can import IFC into Rhino, you can export that, and then you can modify both the geometry of the IFC elements, and you can modify or add new properties to the elements. And this import, export, and modification tools doesn't come with the standard installation of Rhino. You should install that separately. There is more than that, but I am going to talk about two tools. There is this Geometry Gym and Visual RQ plugins that allows you to import, export, and manipulate data, IFC data inside of Rhino. Visual RQ is mostly for the architects, for architectural modeling inside of Rhino, but they have this set of tools that's specifically meant for IFC. And geometry is again more for structural engineers. They have a lot of tools for those, but also they have the set of tools just for the IFC. And if the Visual RQ and Geometry Gym you should buy, it's not for free, but then the Geometry Gym has open sourced this IFC section of their tools, and you can go to the GitHub and get those import export tools for free. Okay, let me go to the Rhino, and I'm going to show how it works. So I'm going to go and import the IFC file. So choose IFC file. Try once more. Okay, we can import just the geometry or geometry with all the parameters. Okay. A little bit of waiting to import all the elements. And the export goes the same way. You just choose one element or multiple elements, hit export, and you get the new IFC file. All right, it's taking a bit long. Hopefully it will get imported. Okay, you can see that 511 elements are imported. Let me switch to the non-transparent view. Okay, I have here some architectural model. Those now are 3D objects which I can deconstruct, and you can change the geometry of them inside of Rhino as well if I like to, but I can do those things also through Grasshopper. So let me go to the Grasshopper, and in this case I will use those Visual RQ tools. So let me open the Visual RQ menu here, and let me do simple example of that. So I'm gonna start with referencing one of the objects from this IFC model. So I'm gonna reference, let's say, this wall. So set one Visual RQ element, and it's done. It's set. I have the reference. Next, I want to read the data of those elements, parameters of those elements. So I'm going to use from the Visual RQ menu. I'm going to use this property name component. I'm connecting the objects in there. I'm going to add some text panel here, and you can see all the properties or attributes that this IFC element has there. But here I can see only the name of the properties, not the actual values what's set there. For viewing the values, I can use the get property component. Connect there. Set one more text panel. Here I need to tell of which property I want to get the value. So I'm going to pick something out of there. It's the wall object number. Let's connect it there. And we have this wall has this attribute set to be VA1. And of course, I could feed in all the parameters there and get all the values there if necessary. In the same way, I can set the properties. I can use the set property component. I'm going to copy this text panel here. So that will be the property. I can choose some value there. So I want to set the new number to be like that. That goes under the value. And here I connect the object there. The thing with the Grasshopper very often is that it's not actually changing something to the initial element. It's just creating new element with new parameters. And it's actually so in this case, for example, if I select here, it doesn't select the original element. It selects element which is just like the original, just that this parameter has been changed. Now, if I now, for example, use some move component here, just to visualize what I'm saying, let's move this element along ZX, say -5 meters. You can see that the original element stays because it's just the copy of that original element. But there is a ways to also manipulate those data of the original elements if I want to. So for that there is a set property. Oh, sorry, not property, but update property component. So, this for now. And I'm gonna, this goes for the property, this goes for the value. Something more there. And here I'm going to connect the original object. So we have the object there. I press the update property, and you can see that it gets updated there. And of course, you can change also the geometry. As I said, you can change the shape, the profiles, whatever you want, and then export the change IFC file. So this is a really good tool for manipulating the IFC files. All right, so let me jump back to the presentation. And last but not least, I want to talk how we can share the data with others and using internet, using the cloud. So one tool that we can use is called Shape Diver. It's a web-based tool. It's not free, but it's free for limited user experience. There is some limitation, but you can share your Grasshopper definitions and models also for free. If you choose the paid version, then you can embed those models and script also in your own homepage if you want. But I'm going to show this free version. I'm going to go now to the web browser. And here I have my Shape Diver account, and I can create a new model there. So I'm just gonna type in the name. I'm gonna let's choose the model which I want to upload, or actually it's not the model, it's the Grasshopper definition. Okay, I uploaded that. Go next. Go next. I'm going to publish. If all goes well, all right. Doesn't went well, so let me retry that once again. As I said, there is some limitations to this free version, and one of the limitations is the computational time. If the script is very big and it takes lots of time to compute, there is some, I don't know how many milliseconds there was, but there is some limitation. Let me try. All right, and let's publish that. Okay, I'm gonna apply the settings. And you can see the same trust script that I showed inside of Tekla, and it reads all the inputs that I have here. And let me try to change something. So you can see the instant result. And in this way, you can easily share your designs to anyone that wants, and they don't have to have any software installed. You just open in whatever web browser they use, you send the link and they can see same thing as you. They can change the controls there, and there is more advanced things that you can do inside the Grasshopper itself. There is the shape diagram menu. There you can specify how you would like those menus to look. You can assign materials, colors to the elements, do all kind of fancy stuff. All right, that's the one thing that I want to show. The second thing is another cloud-based tool, which is called Tekla, and this is essentially the digital platform for AEC industry. That allows you to share the data between the multiple softwares. It allows you to create the, so to say, multi-user Grasshopper definitions. So one part of the script could be on my computer, other part of the same script could be on some computer in totally different part of the world, and we can work on the same script. It allows you to share your data through cloud, through web, and it has a very good open API. So if you know some programming, not the visual but the conventional, like C# or Python, you can extend the possibilities of the whole thing. So, and a very good example to show how does it work. Let me go to the Speckle homepage, and here I'm working with the stream, so I can create the new data stream, create stream, and only thing that I need to do is the copy address of this data stream. So let's copy, going back to the Rhino, I'm gonna open new model. And I'm going to use the same trust script that I used before, Tekla and shape diagrams. Open. Use this. All right, so I have this parametric tracing here. and I want to send this 3D model through cloud. To do that, in the speckle menu, there is a send and receive components. So first I'm going to use send, and I need to define where to send that. So I copied before this address here, and that is the stream name. So under the stream, and here under the data, I connect what data I want to send, what geometry I want to send. And that's it. I press send. If I go back to the this speckle homepage, I refresh that. And you can see that I get almost, okay, not instantly, but very fast. I got the 3D model here. And of course, now I can update something, but in the same way, you could receive data. So there is a receiver. See this? Probably doesn't make sense because I'm working just on my computer now, but it could be, let's imagine it's totally different machine somewhere. So I could use the same stream address there. And I get the data. So to visualize that, I will just move it a bit away from the original geometry. So say for 2 meters. Let's receive. All right, so it's the same truss, but it actually travels through internet. So that's a really great way to exchange your data, your information. And the speckle is not just for sending data. It has links to multiple softwares. It has links to Revit. It has links to Excel. There's really a lot of those links, and you can use this cloud approach to exchange data between the engineers or the other parties that are involved in your project. All right, and then the last thing regarding the cloud, if you are really want to go to advanced level and you know some conventional programming languages like C# or Python or JavaScript, you can use the thing that's called Rhino Compute. And what it allows you to do is actually run the Rhino anywhere or use the Rhino, or rather use Rhino tools, Rhino functions without opening Rhino. And you can run it also on the web servers. So you can generate geometry, manipulate geometry, export something, create PDFs, create ENG on the web server without actually opening Rhino at any point. So this gives lots of power to the users. So, and that's it for me today. I'm going to give microphone back to Eric. So, Eric.
Yeah, thank you, Yanis, for presentation. And before we move to Q&A session, I would like to just to give an idea of the best processes and approaches on how to start using this visual programming, with what to start, what would be sort of typical ways on how to implement that into your daily routines. Yanis, can you confirm that you can see my screen?
Yes.
Okay, perfect. So yeah, so there are many scenarios on how to approach these things. One of it can be self-learning, and then the other is like only to take a services. Yet we have identified one of the main principles and approaches on in other words, steps, what to take in order to bring those visual algorithms into your daily works. So first things first is problem identification, and then by problem I mean sort of identify the possibilities, what exactly, how we can use this visual programming to boost your time, help productivity, and solve some complicated problems. As you notice, there are many different ways and approaches, and there's even more which we couldn't show you in this 45-minute sessions. And of course, we were very broad, but there's quite a lot of options as well. And if you consider that combining it with the C# and other programming languages, it can extend the functionality rapidly. So in any case, this is our identification. It can be together with us. We can arrange a meeting, or it can just be internal meeting where you can sort of brainstorm with the possibilities, what you can do. The second thing is either go straight to algorithm development, which means that when for example, we meet with a customer, we create a specification, understand what exactly we're going to do, what is the sprints on development of this particular algorithm or script or app in general. And then we overtake this development. Afterwards, we typically do the trainings, and the purpose of the trainings, there's actually quite a lot of range of trainings. There's the trainings where we provide basic skills, we have advanced trainings, and we have like light trainings only on how to use pre-developed algorithms. So basically, in general, all of those trainings, as I mentioned, is hands-on and enable to participants really practically approach either continue developing the script, which we have already developed, or just maintain it, or maybe create it from the scratch. So the next thing is, of course, the software. You have to have a Rhino Grasshopper with some plugins if necessary. It's depending on the problem you're trying to solve. And then in the end, there is a support which we provide. And the support is both for the software questions as well as algorithm questions. And support also sometimes include algorithm enhancement, meaning that in case you need to enhance your algorithm, your application, improve something or add some functionalities, we typically doing that during support. Or we are creating a separate specification and overtake other activities. So of course this is one of the suggestions. There's plenty of customers which only focus on trainings and to get their competence into how to approach the algorithms and how to develop them. Then afterwards, when getting acquainted with the system and the capabilities, then create together with us algorithm. Horizontal, you can. There's also cases when the engineers are going very, very deep, and what we do, we typically support into some very complicated questions in the situation when engineer is not capable of solve by himself. So many different scenarios. This is one of the scenario, one of the steps which sort of recommended to take and at least consider when we're thinking about visual programming into routines of structural engineering. Okay, yeah, I guess we could proceed to Q&A questions, and we have a couple of questions. I will turn off my share screen. I will read the Q&A more questions, and hopefully, Anna, you would be able to show and answer to them. So one of the questions is there a way to turn off instant calculation? It was asked during the presentation of somewhere in the middle, in the beginning of the.
You can do that in multiple ways. One, of course, is just to disable the component. It doesn't calculate. Or there is a tool called MetaHopper that you can install, which allows you to add the switch to something. You can switch it off like that as well. So there is a way.
Okay, yeah, thanks. I guess it was also answered during the question. Then we have a question. Are you planning to create similar webinars with more specific topics? And then there's a brackets, my interest in infrastructure segment. So could you maybe comment, Janis, on that?
Yeah, as I said, we are planning to do a series of webinars dedicated to Grasshopper and visual programming. And one could be dedicated also to infrastructure as well. Yeah.
Yeah, then we have one question is, it was also during the demonstration asked, and can we select what Grasshopper component I want to modify? Is there more than one process, for example?
Yeah, actually, I can show this one.
Yeah, I think it graphical representation would help.
Yeah. So it the cool thing about this new Grasshopper component is that it acts like normal Tekla component. So I can input multiple of them. I can say copy this one here. Then I can open the menu for this one and then change the parameters for this one. That's it. Or I can, as I said, they're acting like normal component.
Okay, great. Yeah, then we have one nice note where it says that Grabble frame would be fun and educational tool for structural engineering students, which yeah, I think it's. So yeah, the next question, can I connect multiple softwares into one algorithm? For example, textile structures and finite element mesh design calculating software. So basically 2 softwares at once. Yanis, your microphone is.
Sorry. Yeah. As I said, Grasshopper has links to multiple softwares that includes multiple FEM softwares, and then there's Tekla and Revit and advanced steel and whatnot. And then that way you can really connect to those and send data from one master model to all the others. Yeah, it's possible.
Okay, thanks. Then the question is, can I use this approach to calculate reinforced concrete structures? I guess it was because you showed that steel structures.
Yeah. Using if you're talking about the Karamba, it's there is some limitations, but you can, for the shell structures, you can calculate the reinforcement. That's possible. If you're talking now about the beams and the columns, then you can of course get the forces. You can get the forces in some correct stage, but the reinforcement design itself you should do, for example, in Excel. But it's so easy to transcend the data, so you can, if you have already your spreadsheet that calculates the reinforcement, or for example, if you are using Tekla TEDs, you can send, because the TEDs also has the link with Grasshopper, you can send the data from Grasshopper to Tekla TEDs and do the reinforcement design there in TEDs and get back the results, for example. So it's possible.
Yeah, thanks. The next question, does uploading the Grasshopper file to Shapediver or Speckle also share the script itself?
Not with the standard tools, but for example, with the Shapediver, you can set up in your script file that allows you to download the files, and it allows you to download the PDFs. And I think, I haven't tried, but I think it should be possible to attach as a download material the Grasshopper definition itself. So, and with the Speckle, there's I think no limits. You can send whatever you want, not just from the Grasshopper, but you can send also files through their services. And if I'm not mistaken, and probably there is some limitation to size, I guess, but that's usually not the case with the Grasshopper scripts. They're not that big. So okay. Yeah, there's a way.
Thanks. Then the question is how long it takes to create similar Grasshopper plugin for trusses you showed in the presentation. And the side note is that assuming that you know what you are doing and familiar with the Grasshopper.
Yeah, it's a good question. Yeah. This particular script was created during the training, and of course in the training it takes more, but it's I don't know, it's a couple of hours at most. It's not that. It's quite simple. Quite simple script. It's 2 hours maybe. I don't know.
Okay, I guess we there's not that many questions, but there's still a question about trainings. How long are trainings? And yeah, maybe you can elaborate, because there's actually different type of training. But Janis, could you maybe comment?
Yeah, it all depends, of course, on the type of the training. If you're looking just to very specific subjects of, for example, Karamba 3D or Kangaroo, or we want to cover everything, so it could be anywhere from 1 to, let's say, 3 days, 3-4 days, depending on the topics.
Mm-hmm. Yeah, I would like to comment on that, typically we try to understand the profile of the customer, what exactly he's doing, what his daily activities, calculation, and etc. to sort of adjust the training program and approach it in a way that gives the highest value. Yeah, we have one question for construction from 3D printing concrete. Is it possible to use Grasshopper for design physical behavior of the structure?
I'm not sure about this, how it's, whether it's 3D printing mentioned, 3D concrete, and then the behavior of the structure. Maybe you can elaborate. It's just to calculate like the forces in that and the formations, let's say, in that 3D printed structure, or is it something more specific? If it's just the 3D structure, concrete structure, of course you can calculate the forces. I already mentioned about the limitations regarding the reinforcement, but I guess it's not for the, if it's printed, probably there is no that much reinforcement inside there. So it's possible to calculate the structure itself. Or is it simulate? If the question is about the simulating the printing process, how the layers are being created, it's possible to Grasshopper as well, yeah.
Okay, thanks. And it seems like this is the last question we have. Is it possible to purchase algorithms already developed? And if yes, where I can see function price list? Yeah, very good question.
Yeah. Of course, if you see something that you like in our web page or wherever, we can agree about the terms, and then of course we can, for some fee, we can sell. That's already been done. Why not?
Yeah, thanks. Yeah, because we have like 1 minute left. We also have one question left. We can finalize on that, and all the further questions we would ask you to approach us after webinar. And the last question is, will there be a webinar about optimizing structures using Grasshopper or Karamba?
Yeah, we can do something like that. I have thought about it. Yeah, the optimization is a big topic. A lot of possibilities using Grasshopper. Yeah, we can definitely elaborate on this topic in some separate event. Yeah.
Yeah, I will overtake my share screen to give everybody information about how to contact us and how to approach us, because if you have suggestions or any questions, or you would like to have a meeting with us, and because it's online, so it's relatively easy and straightforward, please give us heads up, send us an email, and we can arrange that. And yeah, and keep posted. We will have additional webinars, well, most likely next year, and we will give you information about them as well. So yeah, thank you everybody for joining. Thank you, Janis, for a very good and informative presentation and answering the questions. And yeah, thank you again, and see you soon. Take care.
See you soon. Thank you.
Bye.